Hi Chem Peeps, this is video 2 on specific heat, and this one's pretty unique. This is going to take several steps because if we look at the problem set over here, it says if 15.3 grams of ice at negative 15 degrees Celsius went to 115 degrees Celsius, how much heat in kilojoules would that take? Now, what we need to do, I have a chart here that I want to use to explain what's going on here. We're starting down here in the ice phase for water. We are going up here in the vapor state for water. So when we look at this phase change or heating curve, we have 5 sections that we must calculate separately and then add together to get the total heat. We first must take ice to its melting point. That's the first step that we must do. So we're going to go from minus 15 degrees Celsius to 0 degrees Celsius, because that's where water freezes and melts. The next step that we must do is we're along the BC part of that line. That change there is where ice and water can either freeze or melt. So we must go from 0 degrees ice to 0 degrees water. Then we're going to go from C to D here. This is the liquid stage of water. So we're going to increase that liquid water from 0 degrees liquid up to 100 degrees liquid. And once we get to this plateau, D to E, we are now on the boiling, condensing, or vaporization, condensing phase. So along DE, we're at 100 degrees. So we start at 100 degrees of liquid and we go to 100 degrees of steam or vapor. Then we're going to go this small section here from E up to F. That is where we're taking 100 degrees of steam or vapor and going to 115 degrees vapor. So there are 5 steps here. When we are in a phase, so this is the solid phase of water, we're going to use the specific heat formula where Q equals the mass times the change in temperature times the specific heat. And we're going to do that 3 times. Here we have the liquid, so we're going to use Q equals mass times the change in temperature times, I'm having trouble getting on the screen here, times specific heat. And then again down here in the gas phase, we're going to use the same formula again. I don't have enough room to write that. And you might be saying, well, why can't we just do it all one step? Because the specific heat at each of these phases is going to be different. So we must calculate those separately. Then at the phase change, solid to liquid, we're going to use the heat of fusion formula, which is going to be the mass times that constant, the heat of fusion constant. And then same thing here, the heat of vaporization, we're going to use the formula mass times the heat of vaporization constant. And then we'll have to add those all up. So let's start with, and of course right here, I have the different values that we're going to need, whether it's specific heat or it's the heat of fusion or heat of vaporization constants. Now, I do want to point something out while we're looking at that. If you will notice right here for the specific heats, they are all in joules and grams, okay, which is common. If you look at the fusion and vaporization constants, they are in kilojoules and moles, and we will have to account for that because our problem is in grams, and we will have to account for that mass, whether it's moles or mass, and we will have to account for whether, when we go to add all 5 steps up, whether it's in joules or kilojoules. So let's start with the first one. We're going to do a change or a specific heat problem where we take the mass, which is 15.3 grams of ice. We are going to go from 0 minus a negative 15 degrees Celsius. Oops. And then we're going to take it times the specific heat of ice, which if we look down there on the bottom left, it's 2.09, and that's joules per gram degrees Celsius or degree Kelvin, it does not matter. And when we multiply through here, we are going to get 480 joules of heat. Now, I'm going to move this into kilojoules, divide that by 1,000, and it's going to be 0.480 kilojoules. Okay, so we have this first step done. Now we're going to the heat of fusion. In other words, we're along line BC. The heat of fusion is going to be the mass, which is 15.3 grams. Now, the constant's in moles, so I'm going to go ahead and just put the conversion here. The molar mass of water, 2 hydrogens, 1 oxygen, off the periodic table is 1 mole equals 18 grams. So that will convert my mass into moles. And then my constant for ice is, or heat of fusion, is going to be 6.101 kilojoules per mole. And you can see the moles will also divide out right here. And then when I multiply across there, I'm going to get 5.11 kilojoules. Okay, now we're along CD, where we're in the liquid state, so we're back to Q. We're going to just have a change in temperature, so 15.3 grams times 100 minus a 0 times the specific heat. Now, that's going to be different than what ice was. It's going to be 4.188 joules per gram Celsius or gram Kelvin, does not matter. If I multiply through here, I am going to get 6,394.5 joules. And if I divide that by 1,000, so that I'm in kilojoules, and I use sig figs, I'm going to have 6.40 kilojoules. Kilojoules. Okay, now we're along line DE. That is where we're in the solid vapor phase, or phase change. That's going to be heat of vaporization. And of course, that's going to be the mass times the heat of vaporization constant. Now again, this is in grams and our constant's in moles. So I'm going to take the molar mass of water, which is 1 mole over 18 grams. And that will get us out of the gram phase, or gram unit. And then I'm going to take it times the heat of vaporization constant, which is 40.67 kilojoules per mole. And of course, those moles are going to divide out. And then my calculator, when I multiply across here, is going to be 34.6 kilojoules. And so we have one step left. Now we are on the EF portion, where we're going from vapor at 100 to a vapor at 115. So we have 15.3 grams times 115 degrees minus 100 degrees Celsius times the specific heat of steam, which is 1.84 joules per gram Kelvin or gram Celsius, does not matter. And when we multiply across here, I'm going to get 422.28 joules. And if I divide that by 1,000, I'm going to get 0.422. I'm going to keep some sig figs here, kilojoules. So our final answer is going to be the sum of each of the sections of heating this ice to steam. So I'm circling all the things that I'm going to add up, and when I add all these up, I am going to get 47.0 kilojoules as the amount of heat to take ice at negative 15 degrees to 115 degrees. I hope that helped. You can find me on YouTube and Chem's Chem Chats, or YouTube and TikTok at Chem's Chem Chats. Leave me a comment if you need to see something more or you like the video, and I will talk to you later.